Okay, guys, we are starting off with number 5, and remember we're talking about L'Hopital's rule, okay? And that is if you get one of those indeterminate forms. So if you try and take the limit and you get 0 over 0 or infinity over infinity, those are the two main forms we're talking about, okay? You try and take the limit and you get one of those forms, we can apply L'Hopital's rule, which says you can take the derivative of the top and the derivative of the denominator and retry it and see where you're at, okay? Now, as we look at number 5, limit as x approaches 0 of sine x times 1 minus cosine x over x squared. First of all, what are we getting if you just plug in? 0 over 0? Because when you plug in 0 for sine of 0 is 0. So 1 minus cosine doesn't even matter. Over x squared, well, that's 0. So you do officially get 0 over 0, right? Okay. Now, L'Hopital's rule is what we're told we can talk about here, right? Now, I guess I'm not doing my job as a calc teacher if I don't throw in the other option. Okay? Because L'Hopital's rule is fine. It gets a little fun with the derivative of the numerator, you know. It's not just a straightforward derivative. But do you guys remember some special limits we memorized?
No.
Well, I don't know if we memorized them, but
yeah.
we became familiar with. One of which was the limit as x approaches 0 of sine x over x. Okay, that was one of our limits. And then I'm going to go ahead here and I'll explain what I'm doing here in a moment. Times the other limit was the limit as x approaches 0. Okay, well, what remains on top? 1 minus cosine x over what remains on bottom? The other x. Okay, those are two special limits, and I don't have a page number written down, or I would tell you a page number, that it was strongly encouraged that you know. Okay? Because, and this is a good, why did I put x approaches 1? I know I said 0. Okay. And this is a perfect spot why. Okay? So here, yes, you can do L'Hopital's, but I'm also going to show you another way here. Because, do you remember these limits?
The sine x over x equals 1, and then the other one equals 0.
Okay. So limit as x approaches 0 of sine x over x is 1 times the limit as x approaches 0 of 1 minus cosine x over x is 0. Well, what is 1 times 0? 0. Okay, you're done with that problem, and here's the deal. If you know your special memorize, or your special limits. I have if you memorize these special limits. So this and this. Okay? Special limits. I'm just going to say that should be memorized. Okay, and that is really sloppy. Yeesh. Now, what if you don't recognize that? Is that guaranteed that you're going to see that split up? No. It's really, really helpful if you do. But if you don't, can we try L'Hopital's rule?
Sure.
We can. Okay. Now, keep in mind, before we try L'Hopital's rule, officially, what do we have to do? We have to state that the limit of the numerator, so the limit as x approaches 0 of sine x times 1 minus cosine x is equal to 0, and the limit of the denominator. So limit as x approaches 0 of x squared is equal to 0. Okay, so remember, saying the numerator and the denominator limits are both equal to 0. If that's the case, then we can take the derivative of the top and the bottom. So let me rewrite this. The limit as x approaches 0. Which way do you want to do this derivative on top? Do you want to do it in the form it's integer, or do you want to multiply it? Like, we could do the derivative. Either way, we're going to have a product rule involved. Or, what if I go ahead and distribute this? Is that okay? Sine x times 1 is sine x, minus sine x times cosine x is sine x cosine x over x squared. Remember, I was kind of shortcutting it on Friday as we got into the things farther, and I said, just kind of said, by LH, that's me stating I'm using L'Hopital's rule, right? Well, let's see what happens when we take our derivatives. It's still going to be the limit, recall. On top, what's the derivative of sine of x? Cosine of x. Now we're going to subtract, and we're doing the derivative of sine x cosine x. How do we have to do the derivative of sine x cosine x? It's a product rule, yes? So with that in mind, okay, so what'd you do? The derivative of sine is cosine times the cosine that's already there. So that's going to be a minus cosine squared x. Now keep in mind, we're subtracting this term, right? So officially, we're subtracting the next term also. Now this time I'm going to keep sine x. What's the derivative of cosine x? Negative sine x. So it's sine x times sine x, which is sine squared x. But now, since we're already subtracting times a negative, it's going to be plus sine squared x. Okay, so that's the derivative of the top. What's the derivative of the bottom? 2x. Okay, remember, it's not a quotient rule with L'Hopital's. Okay. What happens? Plug it in. The cosine of 0 is 1 minus cosine of 0 squared. So that's going to be 1 times 1, which is 1, plus the sine of 0 squared
0
over
0
2 times 0 is 0. What do we just get again?
0 0.
0 over 0. So what's that mean?
Do it again.
Okay, we need to do L'Hopital's rule again. Sorry, you're kind of jumping in. Have you looked at the notes on this?
A little bit, but I haven't pulled them all out.
Okay, so you're kind of jumping in on a big example. Okay, now it looks like I'm running out of room in my box, aren't I? Kind of looks like I kind of slacked off here. And what do I mean? What am I saying that I slacked off? I didn't go through and state. What should I officially be stating here? The limit as x approaches 0 of cosine x minus cosine squared x plus sine squared x is equal to 0. And the limit as x approaches 0 of 2x is equal to 0. Now, good news, as we go to this bottom, realize my denominator, well, you'll see here in a moment. So, the limit as x approaches 0 of cosine x minus cosine squared x plus sine squared x all over 2x. Okay, so we can say by L'Hopital's is going to be the limit as x approaches 0 of, okay, derivative of cosine x is negative sine x. Now, officially this is a minus. Derivative of cosine squared x. Do you remember what to do there?
Sine x. Plus 2 sine x.
Not exactly.
2 cosine x, and then the sine.
Oh, times the.
Yeah.
When you're doing the derivative of cosine squared x, it's the derivative of cosine x raised to the second power. So what do? You take the 2 out front, right? 2, keep the cosine x. Now it's officially to the power of 1, right? And then times what's the derivative of cosine? There's your negative sine x. So that one's going to end up being negative 2 cosine sine. Except what were we already doing? We are already subtracting. So if I'm not mistaken, it's plus 2 cosine x sine x. Right? My answer key agrees. And then plus, we got to do one more derivative. Derivative of sine squared x.
2 sine x cosine x.
This one's going to be 2 sine x cosine x. Because it moved the 2 out front. 2 sine x to the first times the derivative of the inside. The derivative of sine x is cosine x.
Could you add those together?
You can. Okay. All over, what's the derivative of 2x? 2. Well, guys, I know without any more processing, this is not going to L'Hopital again.
Yes.
Because my denominator is 2. Okay? Aiden was asking, could we go ahead and put those 2 together? You can. Okay? I'm out of room. I know my denominator here is going to be 2. Well, here's the deal, guys. This is the limit as x approaches 0. Each of these terms has a sine x in it. Let's make life easy on ourselves. What do you know about the sine of 0? It's 0, yes? So 0 plus 0 plus 0 is 0. And what's 0 divided by 2? 0.
That's what we did at the very beginning.
That is what we got at the very beginning. The very beginning was easier if you caught it, right? That's the huge if, is catching those special limits. Okay? So, you know, a benefit of catching those special limits, of recognizing those special limits and knowing those. Not impossible if you don't know. Okay?
To find.
Just show that it equals 0.
No.
No, we are finding the limit.
Because, like, go back, you find the limit.
If you go back to when we first did limits in Unit 1, one of our primary techniques we will always start off with is just plug the number in.
Yeah.
Okay? You plug the number in, you get an answer, life is good. In this lesson, we're plugging the number in and we're getting something that's not good. You get 0 over 0, that's not an answer. That's what we call an indeterminate form.
Yeah.
Which means it's not equal to anything, it's not an answer, it's not a no solution. It's a you have to do more to this problem to figure out what it's doing. And one of the options when you get this indeterminate form, I don't have it because my bin tree erased over the weekend. Like one of the options, and I don't know if this will just glance at make sense, the very first problem we did, I showed how we could do L'Hopital's. We got 0 over 0, we took the derivative of both. But also, back in Unit 1, this could have factored. And so back in Unit 1, we would have just factored. We would have canceled those out, and then we could have done the limit. This is okay, they don't always factor. They don't always, you know, have that option. And so it's, you know, L'Hopital's rule says if you get that indeterminate form, you can do the derivative of the numerator, derivative of the denominator, and retry. And that's what we did. It was messy, but we did it. Next one's not quite as messy. Okay?
Yeah.
So that'll be a good thing to you. At least not in that sense. Okay, let's look at example 6. The limit as x approaches 1 of ln x minus x plus 1 over e to the x minus e.
Let me guess. You got it wrong.
Well, let's plug in. What do we get? Let's check and make sure that we need to use L'Hopital's. Natural log of 1 minus 1 plus 1 over e to the first minus e. Folks, what's the natural log of 1?
0.
0. 0 minus 1 plus 1 is 0. E to the first minus e.
0.
That's e to the first minus e to the first, isn't it? Which is 0. Are you getting 0 over 0? Do we need to use L'Hopital's?
Yes.
Yes. So now, officially, to use L'Hopital's, not that you have to do some multiple choice, but officially on a free response, you need to state the derivative or the limit on top is 0. So limit as x approaches 1 of natural log of x minus x plus 1 is equal to 0. And split it up, do the denominator. The limit as x approaches 1 of e to the x minus e is 0. And let's go back. And we're going to take the derivative. So limit as x approaches 1, I'm going to rewrite the problem first, of natural log of x minus x plus 1 over e to the x minus e. So by L'Hopital's, the limit as x approaches 1 okay, derivative of the top. What's the derivative of my numerator?
1 over x minus 1.
Derivative of natural log of x is 1 over x minus derivative of x is 1. Derivative of 1 is 0. Over derivative of e to the x minus e. Derivative of e to the x minus derivative of e.
Right, because it would still be basically e to the x because you did first.
Or no, he's a constant.
Is there an x though?
No, there's not.
There's not an x. There's no variable, which makes e a constant. The derivative of any constant is 0. Did they trick us? Of course. They're trying to, right? Okay, guys.
They got me.
Now, oh yeah, we can plug. I was thinking we needed to do something fancy here, but no, we don't. We can plug in. Have you tried plugging in?
Nuts. 0. Wait, is he the one?
What
Just
is
cause
e?
it. Oh yeah, you're right.
So what do you get on top? 1 over 1 minus 1 is going to be 0. What's e to the first?
0.
E to the first is e to the first. E to the first is 2.718, whatever the value of e is.
So equals 0.
Oh, that was natural.
0 divided by anything is
Natural log.
0.
Natural log of 1.
Right?
Will it always come out to equal?
Is it natural log of 1, 0?
Yes.
That's
Sorry, I'm not sure. I missed that conversation, so I'm just answering the question there. I'm not sure what I'm answering.
I
No,
thought you
you're-
said the answer was natural log.
Aiden, if you go back and look at examples 1, 2, and 4 from Friday, we are not always getting 0. Now, does Augie maybe think we always get 0?
Yes.
Maybe. But we're not always getting 0, right? Okay, so. And Augie's just going to have to believe us in our word that you don't always get 0, okay? We'll change it up on number 7. We won't get 0. Okay, L'Hopital's rule here. Okay, it's limit as x approaches infinity. In all personality, I don't need L'Hopital's to do this, but we're going to demonstrate with L'Hopital's anyways. In all, you guys don't need L'Hopital's to use.
Oh yeah, you're gonna use it with some other.
Now, okay, if you plug this in, folks, what are we going to get?
0. No, infinity over infinity.
If you plug it, it's the idea of 9 times infinity squared plus 10 times infinity minus 3. That's infinity. Okay, it's the idea of infinity. On bottom, 12 times infinity squared minus 4. We're getting infinity over infinity here. Okay? So let's work this out the long way, then I'll show you the easy way. Okay, for L'Hopital's, remember, split it up, state your numerator on there. Limit, bless you, as x approaches infinity of 9x squared plus 10x minus 3 equals infinity. And the limit as x approaches infinity of 12x squared minus 4 is infinity. So that's showing we got infinity over infinity. Limit as x approaches infinity of 9x squared plus 10x minus 3. This is me just rewriting the original problem. Over 12x squared minus 4. Okay, and now I'm going to say by L'Hopital's. So now L'Hopital says we're going to do what? We're going to take the derivative of the top, derivative of the bottom. Not to be confused with quotient rule. What is the derivative of the top?
18x plus 2.
Over? Did anyone say 24x?
24x. 24x, sorry.
He had to padlock.
Okay. What's going on here?
Infinity over infinity.
18 over 24.
Okay. Infinity over infinity? Because it's 18 times infinity plus 10?
Yeah.
Over 24 times infinity? It's the idea, and remember, infinity is not a number. It's the idea that those are approaching infinity. So, what do we do now? Restate your official. The limit as x approaches infinity of the numerator. So, if 18x plus 10 is equal to infinity. And the limit as x approaches infinity of 24x is equal to infinity. So now, the limit as x approaches infinity of 18x over 10, or plus 10, over 24x. So we can proceed by using L'Hopital's. And I'm going to have the limit as x approaches infinity. What do we get? Derivative of 18x is 18. Derivative of 10 is 0. Over derivative of 24x, 24. Well, what about the limit as x approaches infinity of 18/24?
Make it 3/4.
Okay. It's 18/24, which reduces to 3/4.
So when it's infinity bounded, you're basically going to your top and bottoms. Gotten rid of the x.
Where some places gotten rid of the x, at least one of them has to have gotten rid of the x. Now, I knew this answer from the beginning, folks,
What?
and you could have too,
Oh, I get it.
because you guys have had me for Algebra 2 and Pre-Calc, and
See.
okay, the idea here, it's what I would call, and what you'll see it labeled as is end behavior model. Okay. We talked about this in Unit 1 in Calc 2, didn't we?
Count two.
In Calc also, okay, there is Calc 2, but that's not what I'm talking about, okay? Now, so in behavior model, think horizontal asymptotes, folks, because that's what it is, okay? If the powers on top and bottom match, the horizontal asymptote is the coefficient.
Yeah.
9/12 are the coefficients. So what we're saying is there's a horizontal asymptote at y equals 9/12, which also reduces to 3/4, there's a horizontal asymptote. My graph is following along that horizontal asymptote as it goes off to the sides.
That makes sense.
Okay? Now, I'm pretty sure we talked about back in Unit 1, when the limit as x approaches infinity, you can just look at your biggest powers. It's 9x squared, and it's, okay, that like connected weird. And it's 12x squared. The rest doesn't matter. Okay, right there you can look and say, oh, it's 9/12, which is 3/4. Is that something?
Yes.
Okay, so that's a good shortcut in that if you caught that, we could have looked at that and been done a long time ago. However, what's my proof here? L'Hopital's works, right? Whether you like me for it or not. Okay. Let's look at 8. I have 2 pages left?
Yeah.
Okay. Okay. Limit as x approaches infinity. Now, if I pause and think about this infinity thing. My top is a typical polynomial. Its highest power is 2. My denominator is not exactly there, is it?
No.
It's not, that e to the 2x doesn't exactly work. So, all else fails, can we look at L'Hopital's probably? I mean, I guess check. 4 times infinity squared minus 3 times infinity plus 2. E to 2 times the infinity plus natural log of infinity. Yeah. Now, I don't know, do you guys remember my trick at the end of class Friday where you could name the top and the bottom as like F and G and then you don't have to keep writing them out?
Yes, we do that.
We can. I have it done in my notes for whatever reason. So this is a trick, is that somewhere in your box, label f of x is 4x squared minus 3x plus 2. G of x is e to the 2x plus natural log of x. It's not even that they have to be f and g, folks. It's just go with what's natural here. So now we can shortcut this, and we can say the limit as x approaches infinity of, what's my top? F of x is equal to infinity. And the limit as x approaches infinity of g of x is infinity. It just saves you writing out the whole thing, right? So, the limit as x approaches infinity of f of x over g of x. Well, by L'Hopital's. The limit as x approaches infinity. Now we have to do the derivative. I need that written out. What is the derivative of the top? Okay. Over, what's the derivative of the denominator?
E to 2x times.
2.
Okay. Pause that. Are we okay there?
Yes.
Derivative of e to some power is e to that power times the derivative of that power. So thus 2e to 2x. Okay, guys.
I want to guess it.
Well, I'm looking at seeing some infinity over infinity action here.
Yeah, I agree.
I mean, here's my thing. 8 times infinity, there's infinity. 2e to the 2x, there's infinity, yes. So are we at the same thing again? Okay. Now, when we state our limits this time, what we just got infinity over infinity was f prime and g prime. So limit as x approaches infinity of both of them, of f prime was infinity and of g prime was of infinity. So you just have to keep straight what you're referring to. So the limit as x approaches infinity, previous it was f prime over x over g prime over x. Okay, guys. Oh, I just wrote that in a different spot. Oh, well. Phi L'Hopital's is the limit as x approaches infinity. Okay. Derivative of your numerator? Okay, something's going to work this time. I'm getting an answer. Fair enough? Denominator. Derivative of 2e to the 2x is 2e to the 2x times the derivative of 2x, so times another 2, so I agree with 4e to the 2x. Now, what's your brain need to decide? What's 1 over x?
X.
Right? So 1 over x is x to the negative first. What's the derivative of x to the negative first?
Negative 1.
Negative 1.
No, negative x to the negative second.
Oh.
So negative 1 over x to the second squared.
What?
X is 0.
Okay. 1 over x is x to the negative first. The derivative of x to the negative first, that's power rule. Negative 1 x to the, subtract 1 negative second, or negative 1 over x to the second. So minus 1 over x to the second. Okay, folks. On top?
8.
8 is 8. On bottom? 4e to the 2x. That's the idea of infinity. Now, it's minus that small little thing, but that's a small little thing. So it's just going to be 8 over infinity. So you have a constant number that's just, stationary 8 over a denominator that's getting increasingly bigger. What's happening to that fraction as my denominator gets increasingly larger? My fraction is getting smaller and smaller and smaller and approaching 0. Or, shortcut that we talked about on Friday, anytime your denominator, you have a number numerator, constant whole number, and the denominator is infinity, it's going to be 0 every time. Okay? So basically a number divided by infinity is 0.
It's negative 0.
This will be 0, I think.
Yeah.
Maybe. Okay. Ready for number 9? Number 9, same thing we're doing, we get to throw in a chart. Because it's AP and AP loves charts. And the table below gives values of a twice differentiable function. Why are they saying that? So you know that it's continuous, you can take derivatives, yada, yada, yada. Use the table to find the limit. If it exists, justify your answer. So, well, let's plug in and see what we're at. F of 3x plus 2 evaluated at negative 2. Well, what's that going to be on top? That's going to be f of negative 4. And what is f of negative 4?
0, of course.
0 on top. I wonder where this is going. Negative 2 squared minus 4. 0. What did we just get? 0 over 0. So, hey, guess what? We've got to do some L'Hopital's rule, yes? So, I guess in my notes I wrote the limit as x approaches negative 2 of f of 3x plus 2. And I guess I wrote it as f of then negative 4 equals 0. And the limit as x approaches negative 2 of x squared minus 4 is also 0. So, the limit as x approaches negative 2 of f of 3x plus 2 over x squared minus 4. So, by L'Hopital's is the limit as x approaches negative 2. Okay, be careful. Derivative of the top. The derivative of f of something is f prime of something,
And then outside times.
and then times the derivative of the inside. So times the derivative of 3x plus 2, which is 3. So what if I say my numerator is 3 times f prime of 3x plus 2? Are you okay with that? I just put my 3 out front instead of putting it out back. The derivative of f of something is f prime of something times the derivative of something. So times the derivative of 3x plus 2, which is 3. Over, what's the derivative of the denominator?
2x.
2x. Okay, plug in. 3 times f prime of, is it negative 4 again? Over 2 times negative 2. Right there, folks. I know I'm doing something. Because my denominator, 2 times negative 2, is going to be negative 4, isn't it?
Yeah.
So we're not L'Hopitalling again. 3 times, what's f prime of negative 4? 8. 3 times 8 over negative 4?
It's 6.
Yeah. Ka-chow.
You just say ka-chow.
Well, we don't do this.
Skadoosh.
3 questions.
Can we do 3 questions?
I think so.
I always think we can, and then, well, you know. Okay, we did a chart. AP loves charts. What else does AP love?
Graph.
Graphs. Let's do a graph. Okay. Use the graph of G, shown below, to find the following limit, if possible. Use proper notation to justify your findings. So, the limit as x approaches 3 of g of x over x minus 3. Well, I'm just going to take a guess. Limit as x approaches 3 of g of x. Well, what is that? That's going to be g of 3. What is g of 3?
2. Stupid. That's how we not do. Wait.
Oh, wait.
What?
Wait.
Timeout.
Yeah, time out for a moment. I should look at my notes more often. Okay, it is 2.
Alright.
Don't ask me. I should really look at my notes more often. Then I wouldn't surprise myself so much. Limit as x approaches 3 of x minus 3 is going to be what?
0.
0. Okay.
Yeah.
Are we eligible for L'Hopital's?
No.
No.
We're not 0 for 0.
It's not 0 0 though.
That we leave right away.
So we done.
Well, we have to give an answer. It's the limit as x approaches 3
There's no limit.
of g of x over x minus 3, which we just got what? 2 over 0.
DNA.
There's no limit. Nice.
The limit does not exist. Okay, I didn't even glance at the answer. Okay, I didn't look at the work, I just assumed we're going to be doing L'Hopital's. However, we didn't need to do L'Hopital's, did we? Okay. And then I started second guessing myself when we were getting 2 there. Okay, moving on. The differential equation for the curve y equals h of x is given by dy dx equals 3x over y plus 2. Given that h is twice differentiable and h of 3 equals negative 1, find this. Okay, now, okay, let's go ahead and check our top and bottom. Limit as x approaches 3 of the numerator, so of h of x plus x minus 2. So what are we going to be doing here? It's going to be h of 3 plus 3 minus 2. H of 3, they told us, yes? H of 3 is negative 1 plus 3 minus 2. is going to give me what? 0 on top. Check your denominator. Limit as x approaches 3 of the natural log of 7 minus 2x. What do you get there? The natural log of 1. And what's the natural log of 1? 0. So did we get 0 over 0?
Yep.
We did. So, L'Hopital's, the limit as x approaches 3 of h of x plus x minus 2 over the natural log of 7 minus 2x. So by L'Hopital's, the limit as x approaches 3. Okay. What, oh what, is that derivative in the numerator?
H prime of x plus 1.
Derivative of h of x is h prime of x, plus the derivative of x is 1, minus the derivative of 2 is 0. Denominator. How do I do the derivative of a natural log of something? Okay. 1 over the insides, right? So derivative of natural log of something is 1 over something times the derivative of something. So what's the derivative of 7 minus 2x?
2.
Negative 2. And where could I put that negative 2? On top of that fraction right there. Do you remember doing that? Okay. Okay. Well, plug in 3 and see what we got. So, h prime of 3 plus 1 over negative 2 divided by 7 minus 2 times 3. Okay. What is h prime of 3?
We don't know.
So what were they saying here? The differential equation for the curve h of x is given by dy dx. So basically, what are they saying here? This is h prime of x here is basically what they were saying. When they gave that fancy for this is the differential equation, that's what they were saying. So we need to do dy dx evaluated at what? So it's at x equals 3. And what's the number that goes with 3? Because we're going to need a y value. Negative 1.
Oh, yeah, you're right.
So if we plug in 3 and negative 1, what do we get there?
9.
We get 9. So what's h prime of 3? 9. Plus 1 is 10. Denominator is negative 2 divided by 1. Oh. So 10 divided by negative 2, which is?
Negative 5.
Negative 5. Oof. Okay.
Next.
One more. Find the limit. If possible, give a reason for your answer.
X to the 99.
Whoa. That'll be 9.
We're gonna have to do that.
Okay. Okay, so what is, you're realizing a problem. Right now, if you do the limit of the top, the limit as x approaches infinity of 2 to the x is going to be what? 2 to the infinity is going to be infinity. But also on the flip side of that, what else do we know? The limit as x approaches infinity of x to the 99th is also going to equal infinity, yes?
Yes. Yes.
So we are at that scenario of infinity over infinity. Now, to get rid of the x in the denominator, you're going to have to do like 99 derivatives. Okay.
X to the 98.
Yeah, we're gonna have to, exactly.
99 times 98.
The derivative of 2 to the x is always going to involve a 2 to the x. If I recall, is it like ln2, 2 to the x or something like that, I think?
Yeah.
Okay, so it's always going to involve a 2 to the x. Is this problem going to resolve itself by actually doing derivatives? No, it's not. So we need to consider this more, what's the word I use here?
D&D.
It says find the limit if possible. I'm just
Yeah.
thinking it's not possible.
If
Well,
possible.
and so I guess, and that's why I was looking to see what notes I had written here. And I did try and consider, okay, which one is growing faster? And technically, if you 2 to the x versus x to the 99. 2 to the x is going to be growing faster.
Yeah.
It's going to be a steeper curve. It's going to be growing faster than x to the 99. So so then you run into the problem of you have the bigger power on top if you want. And that, yeah. Yeah, it just doesn't really do anything for you. So it is a does not exist. It's a borderline one where you almost wonder if there could be an answer, but it is a does not exist.
What happens if you just do the 2 to the 99 times?
You go insane first.
I don't know, because that 2 to the x 99 times is going to get rough. Yeah. So, part I guess I would put here is consider, how did I write that? 2 to the x is ultimately going to be greater than x to the 99 just because it's growing faster, okay? But that's one that I don't know. I don't know if the graph would help us look at that one or not, but yeah. You do end up with a does not exist. Yeah. And they did say find the limit if possible, which, Okay, guys. You are doing L'Hopital's. There's multiple choice thrown in there.
Do we have to show, like, can we just write that it equals 0 over 0, or do we have to do the whole, like, proving it thing?
We know how to do it.
I would at least do it on some of them. Okay, well, and here's my thing. If you go back and look back at this later, I guess as long as you look at notes, you're going to see it.
Yeah.
And if I have I don't remember what I put on the test, but if I have something on the test where it's a free response, not a multiple choice, I'm going to expect you to show it. Okay, so I would to some extent get in the habit of showing it a little bit.
Yep.
Now, are there some of these where you can get away without L'Hopital's?
Maybe.
Yes. Are there some where L'Hopital's just does not apply?
Yes.
Yes. So beware. Okay? And there's some that L'Hopital's will apply.
Good, great.